welcome all of you to the presentation on how we, that is a team, a couple of PhD students from my lab, together with some collaborators, how we beat the world's best drone pilot in a fair head-to-head race using modern computer vision techniques and reinforcement learning for control. So there's a lot of AI in the project, and I'm excited to present this to you as, Cohere AI, former now Cohere Lab. So I think this is the right kind of work to show what is possible if you really want to push the edge and you really have a certain scenario where you want to see how good it is possible to be nowadays. So why do we even work on drone racing? Drone racing is, of course, an exciting sport, but that's not all of it. It's not just fun to work on. Drone racing is a very important task because the task description is simple enough, yet it is very precise, and it allows us to measure progress in a quantitative way. So the goal here is you have 1 or 2 drones, and you want to pass through a course of gates in the correct sequence as quickly as possible. So you need to fly a certain number of laps, let's say 3 to 5 laps, and you need to be quicker than the opponent. So of course, this is a very measurable goal because you can measure lap times, you can measure speeds, etc. And if you're very fast at that, then of course the algorithm is good at flying fast. But before I show you how we can do this with AI, let's have a look at what humans can do on these kind of scenarios. And for this, I want to show you one of the best human pilots racing through a course at the BMW arena in Munich. So this pilot is able to manually fly the drone, only given the video feed that you can also see here in the video at insane speeds, up to about 100 kilometers per hour, doing tight turns, loopings, and all of that. The pilot does not lose orientation or anything. He's able to perfectly fly the drone. So you can really see humans are excellent at this task of flying fast and flying vision-based. And now you can say, okay, that's a cool thing that humans can do it, but is there even any use of why we want the machine to be able to do the same thing that we humans can do? And so the reason that I think this is very important to research this topic is because if a drone flies faster, it can fly farther. Consider a normal drone, something like the DJI Mavic 3 or so, and that thing, like similar other drones, same size, same weight, they will have an optimal velocity of about 16 meters per second. So that's about 50 kilometers per hour. And only when you fly at that speed, you can really achieve the maximum possible range that you can do on a single battery. So if you are able to fly fast and agile, you can fly farther. And that increases the utility of drones. And that, of course, means that we are more likely to be more productive with them and that we can use them better. But flying fast is hard. When you fly that fast, there's a lot of challenges. You have the perception challenges. It can be dark. There's high motion blur. There is also high dynamic range because some parts of the scene can be extremely bright, other parts are dark. And all of a sudden, you can encounter environments where you have low texture. This is not your typical feature-rich outdoor grass, but this can be an indoor building, this can be tarmac, this can be concrete. Then you have the challenges from a controls perspective. In order to be able to fly a drone at those speeds, you need a very high update frequency because drones are inherently an unstable system. If you leave a drone alone and don't give any stabilizing commands, it will divert and crash within a matter of seconds. And of course, data-driven approaches are very well suited for those conditions because the conditions are well defined and we are able to collect data on the exact same conditions. So we can really use the power of neural networks. Before I show you how we do it at the moment and how we beat the champions, let me go back a few years and show how it all started. So what you will see here on the video is a video from 2019. And this was the highest speed that people at my lab could achieve. This was as fast as it was possible to fly. This is model predictive control with some trajectory optimization and a very simple classic vision pipeline. So we run some sort of SVO, semi-visual inertial odometry. So this is something that we achieved back in 2019 roughly, and the drone speed was limited to roughly 3.5 to 4 meters per second. Now, if we fast forward this, then you will now see a video of 2 drones, a blue one being piloted by an AI, and the red one being piloted by one of the best human pilots, Alex Vanover. And of course, I wouldn't be here presenting all of this if the blue drone would be slower. So prepare for an impressive launch and an impressive race between the two. Of course, right off the start, the AI wins a bit, but this is not only due to reaction time, but this is also because the AI is able to directly command full throttle, whereas the human pilot needs a couple milliseconds here and there to adjust. During the lap, you will see onboard views, which are taken from the human pilot, and you will see the AI drone directly in front of it. So the AI drone wins the start, but not only that, is also able to stay ahead of the human and even increase the margin over the course of the race. While at the start, the AI drone to the first gate wins maybe 50 to 100 milliseconds, to the end of the race of the 3 laps, the AI drone beats the human by about half a second. So we are actually able to fly faster also when you consider not just the start, but the whole race. Now, the question is, how do you even do this? And to be able to do this, you first of all need hardware. You need something that is able to actually compute all of the things that you needed to compute to fly autonomously. This is our Swift drone. It features a Jetson TX2 onboard with a breakout board and a RealSense 265, which we use for the images and then the IMU and VIO pipeline. The weight of the drone is 870 grams. It has a thrust of about 39 to 40 Newton. So that gives it the thrust to weight ratio of an impressive 4.5. That means it can accelerate from 0 to 100 in less than a second, thanks to its very high thrust to weight ratio. Okay, we have a drone. So how do we control the drone? Typically, what roboticists would do is they would think about this as kind of a sequential see, think, act cycle, where you have 3 distinct phases. You start out with the localization, and then you have a planning phase and you have a control phase. So during the localization phase, you would run some sort of computer vision algorithm to detect features, to track features, and then do state estimation based on that. Once you have estimated the state where you are at, you would then continue and put this into some planning framework, which computes an optimal path towards the next gate or through all of the gates. And then you will have a controller that is able to track this path. Such an approach gives you a very high explainability, which is awesome, especially as an engineer and you develop it. But the problem is it has very limited robustness as errors do propagate. If your localization is wrong just a bit, there is no way that this framework really communicates this down the line to the planning and control. Incorporating uncertainty is very, very difficult. You would need a quantitative measure of uncertainty and then propagate this through all 3 phases. A much more modern approach, and what some people would call fancy, would be an end-to-end approach, where you just input the IMU signal, so acceleration and body rates of the drone, together with the images into the controller, and then you directly compute the control commands based on that. So this is very nice because it directly maps images to control commands. But on the other hand, it has very limited explainability, because if something goes wrong inside this neural network black box, you don't know what it was. It's just doing the wrong thing. Also, it is very difficult to train such a network, because now if you would want to train it, we would need to be able to render images for the training phase. Or of course, take thousands, tens of thousands, hundreds of thousands of images with associated control commands. But that makes it very difficult. So why not do something in between where we can really combine the best of both worlds? This is the approach that we chose for the paper. Is we have the images in the IMU pipeline go into a classic localization pipeline, which I will talk about in a bit. So this localization pipeline outputs the position, the orientation, etc. So the full state of the drone. And then the state of the drone is used as an input to a neural network, which then computes the control commands directly. So while on the classic approach, you would have a distinct planning and control phase, we have a neural network that does both at once, given the localization, which we obtain through a vision pipeline. So let's start talking about that next. Of course, the classic way to do this, and it's always a good thing to start with the basics, is a visual inertial odometry pipeline, a VIO pipeline. And in the VIO pipeline, we just track features, which we have from the RealSense, and we have also the IMU data together with this, so we can compute some sort of state, a position, and an orientation along with the velocities of the vehicle. But the problem if you do this is, you see in the video below, blue is ground truth, green is the VAO estimate, and you see that as the race goes on, the VAO estimate drifts more and more. And that is a problem, because already after 2 laps, the estimate is off by multiple meters. So just doing a VAO pipeline alone isn't quite enough. But there's a trick to this. So when you look at the racetrack, there are these gates. So we even know where these gates are because that's what defines a racetrack. So why not use these? The idea here was, if we have some neural network that is really good at detecting the whole thing, the whole gate, then we are actually able to use the position of the gate in the image to assist our VAO pipeline and prevent the drift. So now we'll play the video, and you can see as the drone flies, there are some color overlays over the gates, which is the neural network that detects the gates in real time, as well as the 4 corners. And it is able to do this even at the high speeds that you are seeing in the video of about 80 kilometers per hour. So this was really something where having the classic AI capability of pattern finding, pattern matching was hugely beneficial, because handcrafting a gate detector is almost impossible. Training one with a neural network, definitely not. Then, once we have the gate detections, we can use these and simply compute the pose and orientation, positional orientation, using perspective endpoints algorithms. In this case, we have 4 planar points, so we can do this with an IPPE square solution. And we compute the position and orientation of the drone and fuse this together with the estimate from the VAO pipeline in the Kalman filter. So the Kalman filter has both access to the VAO tracks as well as the gate detections. And when you see this in the video on the left, so there is the covariance of the Kalman filter, which always shrinks when it gets closer to a gate. And then when it's further away from a gate, it grows again. So this is an approach that was really nice because we were able to compute the state in real time from the drone. So we have some sort of state estimate. Now, what can we do with this? Well, we need to compute control commands based on our localization. And to do this, we use a neural network. The idea here is, if we have combined planning and control, then you are more robust to perception errors and other problems that can arise during the flight. The control policy itself has access to the state estimate from the VAO pipeline, as well as the next gate position and the previous action. With these inputs, the neural network needs to compute a collective thrust, so that is the sum of thrusts of all 4 motors, as well as a body rate. That is kind of the rate around each of the body axes of the drone that it needs to rotate. And you compute this with a neural network and send it to the drone, and this runs at 100 hertz. So 100 times a second, you send the drone a new control command, and it is then hopefully able to execute the command and fly correctly through the gates. But how do we actually get one of these control policies? What can we do in order to have a neural network that is actually able to fly the drone? And this is where it gets really interesting. What we do here is we use reinforcement learning. Reinforcement learning, of course, especially in the context of robotics, highly successful, because the policy is able, by interacting with some simulation environment, which contains a physics engine and computes rewards for how well the task was executed, reinforcement learning is able, with only these interactions, to come up with optimal solutions to challenging problems, where it is non-trivial to define a cost function, but it is perhaps more trivial to write a simulation and have an intuition for what is a good and what is a bad solution, so for the reward. In the case of drone racing, we use a fairly simplistic reward setup. There is only 4 components to the reward. There's the progress reward, which says, please fly towards the next gate. There is the perception reward, which basically says, please look at the next gate. There is the command reward, which says, don't overdo it. That's the first term. So we penalize the norm of the control command. And also be smooth, so command similar things compared to the last time step, such that we don't have any problems with oscillations. And finally, of course, there's a crash penalty, which says, please don't hit the gates and don't hit the ground floor. If we use these reward components and we use off-the-shelf PPO training, it takes about 100 million interactions with the environment, which is equivalent to roughly 50 minutes of wall time or 23 days of simulated flight time. So the drone really gets a lot of experience while flying because it has, well, nearly a month to train. Also, value and policy network share the same architecture here. Both are pretty small multi-layer perceptrons, 128 nodes per layer, with leaky value activations. So if we do this, we end up with a control policy. And now the question becomes, but how can we even do this whole simulation thing? Because yes, it's nice we have this RL setup, but in order to be able to even do this, we first need a simulation for the drone, because it's not just the reward, it's also the physics engine that is required. And of course, this is into too many details, but I think this is something that gets overlooked a lot in robotics, is how difficult it can actually be to develop these physically accurate simulations that are also good for and fast for training. So I want to spend a couple slides to just give you an intuition for how many things you need to account for when you actually do one of these simulations yourself from scratch. It starts out with the fact that a drone isn't just a motor. A drone is actually way more than a motor. It has a tiny controller on board, which converts the commands you send over the air into actual electrical signals for the motors. And there is a lot of stuff happening here, which has been optimized for human pilots. Well, human pilots have intuition, and they say certain things feel good or certain things feel bad. But unfortunately, what a human pilot likes is not necessarily what is good from a control engineering point of view. And for that reason, you first need to kind of reverse engineer the entire controller and then put the controller that is good for humans also in the simulation, because it doesn't have a negligible effect. In fact, the errors or the challenges this low-level controller introduces can be quite significant. Then going down the pipeline, the low-level controller sends its commands to the motors. So you need some sort of motor simulation. And this motor simulation needs to be accurate enough in order to capture challenging dynamical effects, because otherwise the controller or the reinforcement learning policy will find crazy solutions that are not physically possible and you can never fly. So in order for the control policy to not exploit the simulation, it needs to be realistic. You need a power model, and the power model also feeds into the battery model, such that the control policy, when it is trained, also understands the concept of a draining battery, etc. After that, you need some sort of model that captures the aerodynamic effects as well as the thrust that the propeller generates. And of course, there's various ways you can do this. There is even computational fluid dynamics simulations that some people would maybe say are a good solution here. In the end, we went for something a bit simpler, which is mainly based on polynomials, because this allows us to get a very high speed to run the model at, which is important for reinforcement learning training if you want to be able to collect 100 million samples. So how does it look like? Here you see a video on the left now that basically shows how all the drones, or how the drones learn flying in simulation. In the beginning, there is complete chaos. And then after a while, the drones, in this case, 100 drones are simulated in parallel. In this case, the drones figure out how to fly around the track, and then they slowly converge towards an optimal path. Note, it's not a single line that they converge onto, just because every drone is randomized a bit in terms of its dynamics, its mass, its inertia, etc., such that we can capture a small variety of possible real-world drones that we can fly. So if we do this, we have the physics engine, we have our reward function. Let's see what happens if we actually go and fly that thing. So we now take our control policy, we use our gate detection, VAO pipeline, all of this, we all put it on the drone, and we go fly the drone. If we do that, it turns out that it is a really difficult thing to do it very fast, because we just get a lot of crashes. You can hit the gate in various ways, and most of these ways end with total destruction of your drone. So this is not necessarily something that is very nice if you work on this, because you start fixing a lot of drones. But the bigger question is, why does it even happen? And this is an interesting thing, because no matter how good you are at modeling the real world, every model is wrong. Some are more useful than others, but still every model is wrong. So in the end, we experience a sim-to-real gap, a difference between what we simulate and what happens in the real world. This plot shows exactly that. And there are parts where the trajectories, the simulated one versus the one that actually happens in the real world, are very close, but there's also parts where these two are fairly distant to each other. And there's various reasons for this. First of all, you have unmodeled aerodynamic effects, there's effects of turbulence, and there's downwash from the other drone if there is two drones flying at the same time. But what's much more important than the dynamics model, the physics engine, is actually the perception part of the pipeline. The reason for this is that our camera, for example, as you can see on the video, is mounted on soft dampers. If you do not mount it on soft dampers, you get too much vibrations from the motors, and if you get the vibration, you get blurry images, and also you get problems with the IMU, because the acceleration and rate measurements are more wrong, which then in turn gives you a horrible VIO quality. So the drone doesn't know anymore where it is. Now, if we have this, then there's another part to it. If you have the dampers and the camera moved with respect to the drone, then it now depends on the way the drone turns into a turn. Because if it turns in a very sharp way, then perhaps there's more movement compared to when it turns in a shallow way. All of this means we need policy-specific models. So what we would really need is a model of how the perception pipeline is wrong in order to be able to really capture that when training a policy. So now this is where it becomes interesting, because on the right, you can now see the augmented version of our simulation pipeline. We have this real-world experience thing in there. And the idea is that you deploy policy a couple of times with external state estimation, and then you fly the drone around the track and you record data on how it actually behaves and how its vision pipeline behaves. So when you have done that, you can then go back to your simulation, plug these components in, and then you're able to fly way better. So how does that work in detail? Well, as I said, you first train a policy with the nominal simulation, which means you just do what we did before, but then you do not use the onboard vision pipeline for deployment, but you use an external motion capture system to record how the drone flies and to control it. Because, of course, the external motion capture system does not suffer from problems like camera motion with respect to the body of the drone. Then you deploy the thing and you record the data and fit Gaussian processes to the kind of observation error. So you run the simulation in a forward fashion, and then you see, okay, how much is it different from what I observe in the real world? Or if you don't talk about the physics part, but more about the computer vision side, the question becomes, how accurate is my localization pipeline? What you can see here is a plot where we plot the position error, the norm of the position error, over the course of an entire race. And what happens here is, you see, it's a 3-lap race, and there's periodic effects that happen always at the same time. So there's these big spikes around 30% progress, 60% progress, and then towards 90% race progress. And this is always the same turn. And what you can see there is, it is reproducible. With this insight, we are actually able to fit Gaussian processes to this, and then fine-tune our policy and simulation by plugging in these Gaussian processes into our simulation to fine-tune the policy. And then, of course, finally, you can deploy it with onboard sensing. And with this setup, we can now finally go and race the pilots. When we look at the statistics over the races, so we have the 3 best pilots here, well, two world champions and 1 Swiss champion. If we look at the statistics, it's not like the drone always wins, but the drone wins always on average. So we win more races than we lose. We win 15, the humans win 10, so a 60% win rate is pretty impressive. When we try to understand a bit why are we able to win, let's first have a look at single laps. So this is just 1 lap of the race. And if we look at the distribution here, we can see that the fastest laps of Alex Vanover, our best human sample probably for this race, Alex Vanover is not really slower than the AI drone is, but he has a larger distribution across laps. Humans are not machines, of course. robot is the machine, and the robot is able to fly every single lap nearly at the same performance. So you have a much less of a spread there. The fact that we still have a spread is due to having different control policies and also having a different state of charge for the battery. So if the battery goes more empty, then of course you become a bit slower. But still, the spread is nothing compared to what the pilots have. When we look at a 3-lap race, so 3 consecutive laps, this difference becomes much, much larger. For the AI drone, it is not much of a problem to fly 3 consecutive laps. But for the human, this is really hard to get it perfectly right 3 times in a row, which is also now why even the fastest 3 consecutive laps of the humans are a lot slower, about 0.3 to 0.4 of a second, compared to the AI, just because the human doesn't nail it every single lap. So with this, of course, the question becomes, is it game over? Are we just done with drones and humans shouldn't fly drones ever? Like, is just always use the computer? Is it better? And I think the answer is not really, because there is some of the problems that this work has, I would say, not really talked about or tried to avoid. First of all, while we use identical drones in terms of weight, thrust, etc., we of course need specialized hardware. But this is a huge problem. You need this NVIDIA Jetson, you need the Intel RealSense. And this means that it is a lot easier to just use a standard human FPV racing drone, where you don't need an onboard computer, you don't need a specialized camera, you can just do any drone you want. Also, the human is able to fly almost any drone instantaneously, and while we have given them a full week to train on our track to be really at peak performance, human pilots are remarkably good and remarkably robust. The drone you see here, of course, when it crashes, it's easy to be damaged. The cable can come loose and all of that. It turns out that when human pilots and our AI drone crashed, human pilots were almost always able to continue the race. The AI drone, never. The cable may have come loose, the camera got decalibrated, all of that. So there is really a lot of things that humans, from an intuition point of view, are remarkably good at solving. We see some of the trends now in, well, machine learning, computer vision. They go to larger and larger models in order to be able to kind of cope with this intuition aspect, perhaps. Some argue that if you have an LLM in the loop, then you get a bit of an intuition in some sort. You can use VLMs, all of that. But the problem becomes, if you want to have one of these to fly your drone, you would need a lot more compute. This cannot be done with onboard compute only, because we don't have the capacity to run huge neural networks on board. So naturally, after beating the pilots, the next question was, okay, can we beat the pilots without a special drone? So the next step was, let's try to fly without a Jetson. Let's try to fly with the standard human FPV drone, which has a video transmitter and a front-mounted onboard camera. Right? So we still have a very similar setup to before. We still have drones that have the same thrust, the same weight and everything, but now we also have the same transmission modality as the human. And this is to some extent still ongoing work, so I cannot show definitive results simply because they don't exist yet. But I can give you a bit of a hint as to what is possible in such a scenario. So the video that you see here is kind of an explanation on how we say we want to be able to fly like the humans, just not needing the specialized hardware. And this is by running a much larger model off-board, which extracts complete gate edges from the images. And it does so in an extremely robust fashion. That means we can do this even in a scenario where we have no access to additional IMU information, which would be needed in order to forward integrate that and then have a visual inertial odometry pipeline running. We don't need that. This also means it's possible to just fly on almost any drone, because you just need a video transmission and you plug this into some ground station. Now, with this, I can show you a video how the drone flies. So it starts right in the middle. You see the wooden stand in front of the container, that's where the small drone is on. And now if I play the video, you will see that it flies around the racetrack here. And it flies at a pretty nice speed of about 8 meters per second on the straights. And also on the bottom, you can really see the policy input. So this is everything that your neural network controlling the drone has access to, are these gate detections, which we extract from the racetrack using neural network, of course. But in this case, it's not a small CNN unit anymore, but we actually rely on a much larger transformer-based architecture in order to be able to get the robustness and to also cope a lot better with motion blur, where it turned out that the architecture we had used before struggled quite a bit. As I said, this is still ongoing work, so I can't show a race head-to-head against a human world champion again with this new setup, but I hope that we are able to beat them again, also in terms of lap time, with this slightly more human-like control input modality, where you only get the images from the onboard camera and then do the rest of the processing on a ground station. Having this working out would be a huge success, because then inspection drones, search and rescue missions, etc., could really start relying on more human-like drones that are cheaper to design, faster to deploy, and easier to operate, which I think would also reduce the barrier of entry into a drone-based solution for many real-world tasks. To conclude this and also talk a bit about what I think will come next and what should be worked on next, I think it is pretty clear that if the environment is perfectly known and static, a human is no match for a vision-based drone. We are able, as we've shown in the Nature paper, to beat humans at their own game. The trick here was, of course, to have a policy that is fine-tuned with real-world data and that captures the data in prior runs on the same track in order to really model all the effects of the perception pipeline, all the imperfections there, and also to model the dynamics errors, to cope with effects like downwash, vortices, ground effect, etc., that can occur during the race. If we look at the lap time and the statistics of the races, even though the humans trained for a full week on the track, they never managed to be as consistently as our AI pilot. Of course, this comes as no surprise, because you say that something is like a robot if it is perfectly reproducible. So, of course, humans are not really good at that. Nevertheless, I must say I was very impressed with the human pilots, especially when they really nailed the lap. It was insanely fast, and their fastest laps are as good as what the AI was able to do. But when we look at this in a broader scenario, the big problem is that humans are just clearly superior in terms of generalization ability and robustness. Humans could fly after having a crash, could finish the race with a broken drone. And there is a lot to this. Having a broken drone means not only that its dynamics change, you have perhaps a propeller where a part is missing, you can have different things that go wrong with your drone, but still they were able to finish it. And this means that a human is not only good at flying it at the limit, but also when something changes, due to having a lot of experience, but also physical intuition as to what happens, we can still continue flying. And the crazy thing is, we are not able to do this only at a slow speed afterwards, but we can do this at kind of 100 Hertz in real time. This is something we are definitely currently running short in terms of what we can do in a robotics-based setting. The second thing is, humans don't do explicit state estimation when flying. This perhaps doesn't sound like a big deal, but in research, this actually is. So when we think about it, we are able to beat them on the race course because we have the VAO pipeline running. We have the gate detector that is able to detect all of the gates and use that to correct a drift in the VAO pipeline. However, when a human flies, the intuition is not, oh yeah, I'm at x equals 7 meters, y equals -3, and z is 2 at a velocity of 75 kilometers per hour. But they just go like, okay, there's the next gate, let's fly towards the next gate, let's try to get the turn right. And this is a completely different abstraction of the task. But this is a very useful abstraction. Because when we think about an inspection task, for example, it's also not about being able to fly or to know exactly, oh yeah, I need to fly 30 centimeters in that direction, then continue straight or something. But when you do an inspection task, let's say in a piping system, in a drainage, in a sewage system, you perhaps don't even know exactly what will be in there, but you roughly know when you're as a human, yeah, okay, I need to just fly along the pipe, I need to fly along this canal, whatever. So you have some intuition for the task, and we are able to execute decisions or make decisions based on our intuition very quickly. This is something the AI drone currently cannot do. And if the environment is known, then you get into big problems or potentially big problems with state estimation. So being able to fly only based on images would alleviate a lot of these problems. Also in a feature-less environment where there's just let's say a long pipe or something, a long tunnel, just flying towards the end of the tunnel is a pretty good choice. It doesn't really matter if you know exactly where you are, just don't hit the side walls, which can, if you fly in the middle of the tunnel, you will be fine. So this is kind of a thing where humans have a great intuition for. The AI is at the moment not able to do that. And finally, of course, the task description for an AI is much more complicated than for a human. You need to come up with some reward formulation, and not just for training the control policy in the end. You also need to have some abstraction for the computer vision side here. You need to be able to describe what a gate is. You need to hand design the reward functions also for training that part. So there's a lot of engineering to this, which takes its time. And of course, it's awesome that we are able to fly as fast, but I would still say that in terms of generalization ability, humans are very much superior, and it will take perhaps a year, 2, or even more for drones to be able to just come somewhat close to what human pilots can do nowadays with only 3 or 4 years of training. And with that, I want to end with this picture because it really shows a drone can do anything in terms of trajectories, flight paths, even art. And this is something that I hope that I can work towards achieving for autonomous drones as well. This is also the reason why I have decided to do my PhD on drones and modeling and control for them, because I believe that they are extremely versatile. They're awesome vehicles, they're fun to work with, and they have so much potential that can still be unleashed. Thank you very much for giving me the opportunity to present here in the Cohere setting.
Thank you very much, Leonard, for the presentation. It was very enlightening. Yes. So, does anybody have any questions? Do you guys have any questions? Mayank, do you have any questions? So, while the guys are coming up with their questions, I just wanted to say that when we spoke earlier, I said that I like high-speed racing, right? Which is why I find your work interesting. But there is another reason why I find it interesting. So my background is in chemical engineering. And in chemical engineering, we talk about process control quite a lot, and we try to do a lot of automation. And there are a lot of circumstances where we do not really have the ability to function directly. So there are certain environments where automation is the best way to go. For example, you are in a high pressure environment, or you are in a corrosive environment where you're dealing with a lot of corrosive materials. In such environments, the best way to go about it is either you find some means of simulating the environment. So for example, if you are dealing with corrosive materials, instead of having a human being having to handle such materials, why don't you come up with some kind of way of simulating the whole process? That is basically where digital chemistry comes in. If you've heard of that. I don't know if you've heard of digital chemistry. Can you hear me?
Yes. So
yeah,
I think it always depends a bit on the domain, right? So the things that you're describing now are very much in a different setting compared to what we've done here with the drones, right? So also the solutions naturally need to be different, because aspects that say you talked about corrosion, chemicals, etc., there is safety involved. Right? With drones, of course, especially in the research setting like this, safety is ensured by having a net and no one in there. So this is a lot easier to kind of have these. So I think you really need to think about the constraints of the solution when you try to come up with them. And one of the things I think you can take away in more in a general setting is if you know the problem that you want to look at, that you want to understand, or that you want the robot, some autonomous system to help with, then you're in a very good spot if you can also change the environment in a way that it's suitable for the robot. If you want to have them just replace something, this is always a lot harder. It's like with the drones, right? You have the drone race, we do autonomous drone race, that's cool, but we use our own hardware. If you want to really have a plug and play replacement, I think that's independent of the field and the constraints. That's always the hardest thing, because we have optimized the world around us for ourselves. So, well, replacing us one-to-one is always difficult, but if you have the flexibility to get the same outcome in a maybe slightly different way, I think it's a lot easier, independent of the task, right? So that's perhaps, yeah, for industrial environments especially, I think this is quite relevant to also consider.
Yeah. Funny enough, I recently spoke with a couple of friends. They were working on a project. They're actually undergraduates, and they're marine engineering undergraduates. They work in marine engineering, and then they're working on their final project where they are kind of having to build an underwater drone from scratch, basically. And I found it interesting. I found it fascinating, and so that was part of the reason why when the topic of your presentation came up, I was like, wow, this is quite interesting, something that I would be interested in seeing. And so thank you very much for being here with us at this time to share your work with us. It's very amazing. We are honored that you would take the time out to be with us today. So Mayank, I'm still waiting for the moment where you drop that question.
Yeah, I was wondering, with the RL policy that you are trying to train your models with, so like, is the I think so you might be using on policy settings here.
You mean
In what sense? Like
yeah, for the training, like taking the images and trying to train. So is it on policy or a off policy setting here?
So it's a standard PPO setting, but
okay.
What I want to correct is we don't use the images for training. The training is state only. If I would have to render images, I would have to go for something that I couldn't use PPO just because of its sample inefficiency. Then we would need something way more efficient, say SAC. Yeah, probably something in that direction, or perhaps even more towards now the modern. There's more modern like Dreamer architectures or so you can also use for having images to control commands. I think we would really have to change that part quite a bit, because if generating samples isn't cheap, using this off-the-shelf PPO approach is not a good thing to do.
Yeah, true. And so, plus, what is the the effect of calibration from sim to real? Is it much when you're trying to train, or how is it like?
Yes, so I mean, when we had the slide on, let me just quickly jump back to that. So we had
I think from the presentation, I think if I remember correctly, the deviation was more pronounced the further along the race went, right?
So you have the most pronounced differences in terms of modeling error, of course, when you consider the perception pipeline here, where you actually talk about position. So the position error during the race can be up to about 1 meter, where the perception pipeline gets it wrong. This is something that causes the most problems in the sim to real gap. When we talk about the dynamics mismatch, we still talk about 30, 40 centimeters that we end up in a different spot due to that, especially during the sharp split S-turn where we have to like fly top down. But apart from that, we typically have the largest problem with the perception pipeline. Most of the sim to real gap, and I would say 1 meter is typical what we get due to the elasticity of the system.
Yeah, that's true. I think so. Using Gaussian processes to it's like faster as opposed to using like other alternate algorithms which are like uh, for the computationally faster on uh, the, uh, the real world and training which you kind of take into account here. So
Yeah,
that's
definitely.
yeah.
Speed is everything, right? If you train with
Mhm.
PTO, speed beats precision. It doesn't matter if you're precise, you need to be fast. And a bit of domain randomization will take care of the rest.
Yep. So I
Okay.
have a big
Okay.
query here with respect to, since like you might have broken many drones during the training and like played around. So like how much
You
is the
can't you can't
cost
you can't get omelets
associated?
without breaking eggs.
Yeah.
You can't get
So
omelets without breaking a lot of eggs.
yeah, but like since it's costly too, since the cameras, the drone wings, and the other components plus the batteries. So like, how is it? Like, how do you guys manage it? You have to ask for your funding from your university, or like, how do you keep coming back to it when the cost is a concern here?
So I think
And then it's kind of weird. It's kind of weird where you say, "Hey, I need funding. Why? Because my drone crashed. I need funding to get another drone that will probably crash again."
Yeah.
no, I think one of the most important parts is that you're a good mechanical engineer and you're smart about your design. So you've seen that certain plastic parts are around the computer. These are then printed with nylon, for example. They have dampening designs. We have kind of structural softness where the structures can absorb a lot of energy due to the way they bend. This is just up to you as the person who designs the drone. So you talk to, you do this in collaboration with people that really know materials. You have some 3D print experts typically around, and this already mitigates a lot. Then you want to choose hardware that's robust. That is the single reason why we love the RealSense so much as a sensor. These two T65 tracking cameras are unbreakable. It's the most robust thing I've ever seen. And if you think it's broken, you open it up, you plug in the cable again, and it usually works. These things are insanely robust.
Oh, okay, cool.
Okay.
So I would say we have broken a lot of drones, but typically propellers, they're cheap. 3D printed parts, they're also cheap, and not too many computers. So I would say if you're smart about the way you test, the way you design the drone, you can mitigate quite a bit of this. And then it's only work intensive to screw them back together. Have to replace all the 3D print parts, all the damping materials, and so on. But it's not necessarily costly in terms of money. So I wouldn't say that you need a lot of funding just to be able to afford all the broken drones. It's not something where I would subscribe to. You can do it with, I would say, probably 10 computers throughout the whole time that we did it. Maybe 10 to 20 breakout boards is the maximum number that we've used up. It's not too bad, actually, if you're smart about what you do.
Cool. So I have this Ford 35i, and since this is a depth RealSense camera, and so like I have used this for simple robots training and like the depth sensing and enough. So like I would like to ask, does the depth also comes into play, since like it's flying at 80 miles per hour or kilometers per hour? So does that also keeps my query is, so do you also take depth into account here? So no.
We don't have a depth camera, so we don't have the 435. We have the 265 RealSense on board. There's two problems if you do depth. One, field of view. Most depth cameras give you a fairly narrow field of view, say 90 degrees kind of opening angle is what's typical around that. Our RealSense camera has 170 degrees diagonal field of view. That's completely different amount. So you get a lot more environment. Second, depth sensing at the moment suffers from the baseline problem that you kind of run out of baseline after like 6 or 7 meters in terms of distance. And our drone racing track was 20 by 20, roughly, in terms of outer size. And there is no depth features if it's not a gate. So it's just a planar floor, it's planar walls, it's just a box that's too far away to be sensed normally. So I would say depth can be a very promising avenue, maybe a LiDAR even. But for the work as we have done it now, we didn't use it because the limitations of the sensors kind of outweigh all possible benefits of depth.
True. Thanks.
So, Leonard, I have a question. Thank you very much for the amazing answers. I just have one extra little question. Have you thought about how maybe using event cameras can kind of change the pipeline? Is it something that you guys considered?
Yes. I mean, the lab has a couple works on event cameras with drones. One of the earlier ones I remember now on the top of my head was where we, 2013, I think, we had event cameras and they were used to kind of spot markers. So you would get kind of a rough pose estimation. We also have recently done a version 2 of that system with like more accurate pose estimation. Then we have the, of course, Dodge drone paper, Science Robotics, where you had an event camera and it would detect like if a ball is thrown into the flight path of the drone, and then it would be able to avoid. So we have some experience putting event cameras on drones, but there is inherent limitations with them. One, if you fly really fast, you get a lot of events, and that can be a problem because too many events is not so good. These sensors have a certain readout limits, which is just hardware limitation of the sensor. The second aspect of event cameras, unfortunately, they're very expensive and very brittle. So it is quite easy to break these things, and they're very expensive to buy, and they're quite, bulky.
Fair enough.
More recently, we have had smaller cameras being released. DVX Explorer is probably a good one. Innovation makes this camera, and those are much, much smaller event cameras. But when we did the work, most of them were too bulky, and also it's truly the limitation with the streaming of events at those high speeds that can cause issues and takes a lot of compute and bandwidth to process.
Okay. Thank you very much. I just thought about it. I was like, okay, let's see what would an event camera actually do here. Perhaps it would be beneficial for easy detection of the gates or something like that. So I just thought about that, and then you answered my question. So
gates, yeah, I think also opponent drone would be really nice because the propellers spin faster. So you would be able to perhaps detect the spinning propellers based on having a higher event rate than most other things. There is a 2021, I think, or 2022 ICRA paper with that idea where they try to detect drones with an event camera. And it's actually quite easy to detect a drone if you have at least a static event camera, because the propellers trigger so many more events compared to everything else that, well, just find the 4 most triggering points, and that's the 4 propellers, and so you know it's a drone. So there is things where event cameras are pretty cool for in this setting.
Yeah, that's actually quite an interesting idea. Basically, counter-espionage or something. Yeah, I wouldn't mind if you could link that paper for me. It would be nice.
Which one? The event camera?
The 2021 paper you just discussed. The one you just discussed.
Sorry, I didn't get which paper do you want more details?
Yeah, the one on the event camera with the drone detection.
Yes, but I will look it up. It's not from RPG. I think I need to remember, but I'll send you an email afterwards, and then you can link it in the description.
Yeah, thank you very much. That would be nice. Yeah. So thank you very much once again, Leonard. I'm putting out the call for questions once more. Does anyone have questions? If there are no questions, then I think we can wrap this up. So Mayank, do you want to do the wrapping up?
Yep. Thanks, Leonard, for that interesting and awesome presentation. We enjoyed it a lot, and certainly I learned a lot from this. Let's call it a call, and we will meet you again later. Bye. Take care.
Right.
Yeah.
Bye.